In this video, we're going to introduce integration of selected logarithmic and trigonometric functions using formula that may include differentiation. That means we're not going to do integration to find the integration of a function. To start with, let's introduce the first hypothesis. For f of x equals to ln of absolute value of x, the integration of f of x can be reached using the following formula. Integration of f of x dx equals to x multiplied by f of x minus e raised to the power f of x plus constant. Based on the above hypothesis, integration of ln of the absolute value of x dx should be equal to x ln absolute value of x minus e raised to the power ln absolute value of x plus constant. And this is equal to x ln absolute value of x minus x plus c, where x equals e to the ln of absolute value of x. And we're just using x because the ln will produce only positive values and receive only positive values as a function. Now, to prove the hypothesis, let's use one of the following integration methods, because hypothesis has to be proved. So to do so, we need to integrate ln of the absolute value of x dx. Let us use integration by parts. Since we cannot split L of x into two parts, let's multiply it by g of x equal to 1. So we will be integrating g of x multiplied by f of x dx, and that should be equals to integration of 1 multiplied by ln of absolute value of x dx. Now let du be equal to g of x and v equal to ln of the absolute value of x. Hence, du equal to 1 implies u equal to x, and for v equal to ln of absolute value of x, dv will be equal to 1 over x. Consequently, the formula for integration by parts is integration of v du will be equal to u dot v minus integration of u dv. This implies that our integration of ln of absolute value of x dx equals to u multiplied by v. Our u is x, our v is ln of absolute value of x, minus integration of u dv. Integration of u is equal to x, and dv is equal to 1 over x dx. So we can see that we can cancel the x's, and if we do so, then we will have integration of 1 dx, which is right here. So integration of 1 dx. So the end result will be equals to x ln absolute value of x minus x plus constant, which is consistent with our hypothesis. So thanks to the hypothesis, let's go ahead and check our second hypothesis, which states the following. Integration by differentiation of f of x equal to arccotan of x is given by the formula x multiplied by f of x plus half of ln of the absolute value of 1 divided by the derivative of f of x plus c, where c is the constant of integration. To start with, let us find the derivative of arccotan of x. If v equal to cotan inverse of x, then the derivative of v will be equal to the derivative of cotan inverse of x. Also, we can conclude cotan of v equal to x by taking cotan of both sides of this equation. So cotan of v equal to cotan of cotan inverse of x. That implies cotan of v equal to x. Let's relate cotan of v equal to x to the following right angular triangle. If we look at the angle v, so its cotan will be equal to the adjacent divided by the opposite, and that will give us cotan of v equal to x, consistent with the statement that we have over here. Next, we have to do the derivative of cot of v. We know that cot of v equal to x, so derivative of cot of v should be equal to 1. So we have derivative d by dx of cot of v equal to 1, but then we can expand v and we will get derivative of cosine of v divided by sine of v. And this is a quotient, so we have to use the quotient rule. And we will also have to use implicit differentiation. To do so, we're going to go ahead and get the result. Final result will be equal to negative cosec square of v multiplied by dv by dx. So we started from the derivative of cot of v and we went to values that are equal all the way to the end. So we're going to take from 1 and we're going to equate 1 to the last term. So therefore 1 equals to negative cosec square of v multiplied by dv by dx. If we solve for dv by dx, we will get dv by dx equal to negative 1 divided by cosec square of v. We can find cosec square of v from the triangle. Since this angle v, cosec of this angle will be equal to square root of 1 plus x squared divided by 1, which is equal to square root of 1 plus x squared. Now we're looking for cosec square. That means we have to square this square root. We'll end up getting cosec square of v equal to 1 plus x squared. Based on our hypothesis, integration of cot inverse of x dx equals to x multiplied by cot inverse of x plus half ln of the absolute value of 1 divided by f prime of x. So f prime of x, that means dv by dx, and we showed that dv by dx is equal to 1 over 1 plus x squared. So dv by dx is the derivative of f of x. So we have to get the reciprocal of the derivative to get 1 divided by f prime of x. And that reciprocal will be 1 plus x squared plus constant. And that is what we claim by the hypothesis to be the integral of the left-hand side, or the value of the integral of the left-hand side. To prove this, we have to perform actual integration of the left-hand side and prove that it is consistent with our hypothesis, and that will prove our hypothesis. So our proof will start by looking at negative 1 divided by cosec square of v equal to negative 1 divided by the value of cosec square of v, which is 1 plus x squared. We just explained this one, and it's equal to dv by dx. If we look into this line, we can see the three components over here that are equal. It's just that we have them in different order. So we started with negative 1 divided by cosec square of v equal to negative 1 divided by 1 plus x squared equals to dv divided by dx. If we solve for dv from this equation, then we will get dv equal to negative dv dx, negative dx divided by 1 plus x squared. Now let the integration of cosine inverse of x dx be equal to integration of 1 multiplied by cosine inverse of x dx. If du equal to 1, then u equal to x. And if v equal to cotan inverse of x, then dv equals to negative dx divided by 1 plus x squared. Therefore, the formula for integration by parts, which states integration of v du equals to u multiplied by v minus integration of u dv. It implies if we plug in all the values over here, we can see that the first here integration of v du, our v is cotan inverse of x and our du is 1. With respect to dx, the integration will be equal to the first term, which is the product of u multiplied by v. So our first term, the product of u, which is equal to x, multiplied by v, which is equal to cotan inverse of x, minus the integral of u dv. The integral of u, our u is x, our dv is negative dx divided by 1 plus x squared. So our integration over here is integration of x multiplied by negative 1 divided by 1 plus x squared dx. Now to perform this integration, we have to use integration by substitution. Let w equal to 1 plus x squared. Hence, dw will be equal to 2x dx, and solving for dx, we'll get dx equal to dw divided by 2x. Since integration of x multiplied by 1 divided by 1 plus x squared, it could be done using integration by substitution. Then we will substitute, instead of 1 plus x squared, we'll substitute w. So the integration will be x multiplied by 1 divided by w. And then instead of dx, we'll use its value, which is dw divided by 2x. So our integration will be half integration of 1 divided by w multiplied by dw. We know that integration of w with respect to dw will give us ln of w. But then ln of w, we know w equal to 1 plus x squared. So the end we're going to get is the answer of this integration is half of ln of 1 plus x squared plus the constant of integration. We didn't put the absolute value because 1 plus x squared will always be positive. Now, it then follows that integration of cotan inverse of x dx equals to x cotan inverse of x plus half of ln of 1 plus x squared plus constant, which is consistent with the one that we reached by using our formula, thanks to the hypothesis which uses shortcuts. If you like this video, please go ahead and subscribe for the channel, and you have a great day.